Okay, welcome to our presentation about the Fudge Factor. So, what we did was that we understood that fudge is a very sensitive process, right? You don't want to burn the fudge, and you want to make it so it reaches the right temperature so it actually sets, case in point being this fudge.
This sad attempt, which is for you.
Which did not quite get to the exact right temperature and didn't set quite as well as is desired. So we figured that we've all made fudge before and have eaten fudge before.
Quite a bit.
And we know what qualities we want in our fudge. So our goal was to make a temperature control to make the perfect fudge.
Okay.
So our model was pretty straightforward. It was just a basic energy balance. So we have our accumulation over here represented as the change in temperature of the fudge. That's our accumulation of energy in the system. And then this is our energy input, which came from the heat transfer through the stove element and then through the pot as well. That is controlled by this Q, which is the power given to the stove element. And then here we have the efficiency of that stove element, which we found through literature values. So this is the energy into the system. This is then the energy out of the system, which is where our disturbance variables come in. So we have our free convection and then our forced convection here. So the disturbance variables we have there are the temperature of the ambient air, which will change the heat transfer out, and then also the velocity of the ambient air. And through a very fun, painstaking process, we were able to simplify this down and get 3 transfer functions out that we then plugged into our Simulink model.
Mm-hmm. So here is the Simulink model, just to simulate it a little bit. As you can see, we used a PID controller. There's our first function, there's the ambient temperature and the air velocity. All it did was just, a nice simple feedback loop, and what we did is we converted it from, I believe it was from temperature, just nice basic Fahrenheit, over to watts from the stove output. Went over that, had a nice display right there just to give us a thing. We put that all into a MATLAB file, which I compiled into an Excel spreadsheet. And here are our output graphs. This is the actual control right here. So as you can see, just a nice good up from the ambient temperature, the nominal temperature, to our set point. It took about 18 to 20 minutes, which is a little bit more than when we have an expert sitting there, monitoring the temperature constantly. And so, but we said, the chemistry of fudge making really likes this nice slow rise time, gets it in there, and it sets the fudge quite well, and it's able to account for the disturbances, so it keeps it at that set point without you having to adjust anything. We did some stability control on this. And if you cranked the gain up too high, all it would do is it'd burn the fudge really quick. And, that's the end of your fudge. It didn't react exothermally or anything or take off, so it was pretty stable, not too dangerous. And then if you set the gain below 0, it just turned off. We had the controller set to where it wouldn't go below 0, and so our disturbances just kind of slowly cooled it. So, nice and safe, good fudge making. Can't really hurt yourself too much with the PID controller.
Yeah, so in conclusion, our model rejected the disturbances that there were, and we figured that the non-hassle of having an automated fudge thing was worth the short time cost. And yeah, that would be appealing to amateur fudge makers as well, such as ourselves.
And I can make fudge.